So welcome to i3 TV. I'm joined today by Reuben Mungai. Reuben, tell us a little bit about yourself.
Thanks, Damien. So I'm an associate director at i3 Solutions with a bias, I would say, to electrical engineering, electrical. I do have a background in physics. I went to school in the States and also did my initial power engineering, or my initial introduction to critical systems in the States. Started doing data centers for banks out in New Jersey, and then moved to London about 5 years ago with my family, and yeah, got into the data center industry here, and it's been building data centers ever since.
Brilliant. So we're here today to talk about arc flash. Let's just dive straight in there. Reuben, what exactly do we mean by arc flash?
So an arc flash is basically any it's any arc caused by a high voltage gap that causes an electrical current. The arc is caused by the ionization of gas, so any form of gas. So air is gas. So the arc and the flash will be released when the gas is ionized and the electrons flow, and those release photons, and that releases the shock wave due to that high voltage.
So how common would you say arc flash occurrences are in the data center? It's not like I feel there's an epidemic of them. We're not hearing about them every day.
Yeah, so it's reasonable to assume that the number of arc flash incidences in data centers is not that high, and it's also hard to collate and to collect the numbers due to the sensitivity within data centers themselves. But it is reasonable just to the history of arc flashes coming from the United States is due to the voltages and the currents that they use out there and how they build their equipment. So due to the number of occurrences out in the States, the adoption of arc flash risk analysis is due to the end users who end up adopting data centers in Europe. But the incidences themselves are not that. I wouldn't say there's not a lot of, you don't see that a lot in the news where you have arc flash incidences. So I don't think it's a big occurrence out in data centers.
What are some of the implications of arc flash? What kind of damage can it do? What are the challenges for the data center industry?
Well, data centers now, especially hyperscale data centers, are high energy density data centers. So we need to bring all that energy through and distribute it through the data center. Now, an arc flash occurrence, one, of course, is the human life element, right? So operators who are working on sensitive or on equipment that's powering IT equipment that that requires less downtime. Most of the time they'll be working on live equipment. So you have huge density of energy. So you want to make sure that your operators are safe when maintaining stuff, right? So the main thing is safety and safety and health of your operators. Because one, if anything wrong happens in the data center, you assume that a data center is this high secure, like everything is made to almost to a sense of perfection, right? If you walk into a data center, it's one of the most cleanest, most organized places. So you'd expect that should be carried over to the health and safety, because it's at the end of the day, it's about people. And if an incident like an arc flash happens at a data center, it raises the question of one, right? It's your reputation, right? How if you have arc flash incidences, so accidents can happen. The question becomes is how did you mitigate it? Did you mitigate it? Because arc flashes are normally it's a human element. It's normally due to human error most of the time. But the downside is, right, you have loss of equipment. It takes a long time for you to replace that equipment, or you end up having somebody getting really hurt, or you end up having a loss of life, and you have to deal with that. So the PR repercussions, right? So you end up having all these repercussions, which might take a blow to your name. So just so that you could have the functional part where you have loss of IT or a loss of your systems, and then you could have the other part where it affects your reputation and how you're seen in the industry.
Got you. And is it a sort of a reasonable thing to say that with the proliferation of data centers, because there are now, an increasing number of large data centers being built, and that trend tends to be accelerating, if we're not careful, we could expect there to be more challenges from things like arc flash?
What we've seen is as data center builds have accelerated in Europe, luckily that acceleration being pushed by American clients has necessitated the inclusion of arc flash within the arc flash studies to mitigate any occurrences, right? And if you compare how systems are built or how equipment is built in Europe versus how it's built in the United States, where this originated, there's more standards here that basically recommend that equipment be compartmentalized in different ways to help and to mitigate arc flashes. So if there was data where we could compare, right, the arc flash incidences in Europe versus America prior to hyperscale data centers coming in, I would feel like the numbers would be low, because that was my first comment when I moved here, when I saw a panel, was how structured it was. It was one of the most beautiful things I saw versus coming from America, where our stuff looked like a tin shed. So it would make sense why you need arc flash in the States, and why here there's more robust, and there's more I think there's more thought put into making sure that the equipment is resilient in a way that it already protects the operator.
Reuben, you mentioned risk assessment. What is the role of risk assessment in mitigating occurrences of arc flash?
Well, I guess risk assessment is our best effort. Is our best effort to try and mitigate incidences that we know could happen due to the amount of energy that we're bringing into a data center, right, or into a building, housing this equipment. So the risk assessment allows us to see what the expected energies would be, because when those arcs happen, they release a lot of heat because of the resistance the resistance through the air as it ionizes the air, where you have electrons, releases a lot of heat, and this heat gets almost all to the temperatures of the surface of the sun. So the risk assessment allows us to see the incident energies that operators might be exposed to when working on live equipment. Now, you got to remember that the risk assessment is only for operators working on live equipment. So, and that's if a panel is closed, it's not live to me. It's when it's open and exposed and it's still on, that's when it becomes live to me. So the risk assessment is to basically show us, okay, where within the system do you expect to see high incident energies, right? That could cause burns, more than second-degree burns. So the whole point is for the risk assessment is, okay, where within the system do we have energies that would cause second-degree burns, and then how do we mitigate where they're larger? Then where those incident energies are larger, how do we mitigate that? And so the risk assessment will give us that, and it will also give us the tools and the equipment that the necessary operators need to protect themselves while working on equipment with high incident energies.
And who's going to perform the risk assessment?
So the consultant performs the risk assessment. So the consultant or whoever who's looking at the power system design. The risk assessment is a mixture of how the elements within the system work. Now, circuit breakers, as the word entails, is to break a circuit, right? So we look at how we can arrange the control topology of the circuit breakers within the system such that it opens where there's an arc. If an arc incident happens, how quickly can we open that circuit breaker closest to that arc so we can extinguish it, right? You extinguish it by by putting off the energy that's coming through it. The energy is coming from the circuit, from the source. So by opening the circuit, you basically kill the source and you extinguish the arc. So we go through the system seeing what do we need to do to compromise certain things, right? We need to compromise certain things to make sure that the system is safe, and in a way, we make sure that the incident energies are as low as possible. So the engineers, it's literally power engineers, right? So you have power engineers who go into the system, putting all the controls of all the breakers, and then seeing, okay, what do I need to tweak to make sure I can make the incident energies as low as I can. And then if I can't, I add other solutions within the system to make sure that I can open or extinguish that arc as quickly as possible, which is basically by how quickly can I open that circuit breaker? You know, how quickly can I get information that will help me open that circuit breaker, for example? So that's what you have technologies like light sensors, right? We just talked about the arc flash. So light is the fastest thing that we know in our universe. So we have light sensors because the arc is normally accompanied by a flash. So you could put light sensors within your system such that when the light is seen, it opens the circuit breaker. So that is a very quick reaction, and that will extinguish the arc before it becomes too dangerous, where it could cause more than second-degree burns.
And it's the role of the person creating the electrical design to do this, or is it something that's reviewed by someone else to ensure, you know, are there checks and balances in the design process to make sure that these kind of mitigating structures are put in place?
So that, yes, there will be checks and balances within the engineers themselves. So the engineers who've been tasked with doing the analysis, they'll make sure that they've done their due diligence. And then if we go through the process of peer review one to the next stage to the client, or most of the times with data centers, they'll hire another consultant to go through the design to make sure that the things haven't been missed and that it's mitigated to the standards that the end user wants or whoever's going to adopt the data center requires.
Yeah, you touch on standards. So what legislation exists in EU and in the US to increase worker protection from arc flash?
So in the US, there's the NFPA standards, the NFPA 70E standards that basically have been adopted in the EU. In the EU, they're not really standards specifically related to arc flash, but in the States, they are. What you see is an adoption of those NFPA standards and how to use, and also with adoption of the protective, the PPE, the protective clothing, that the personal protective equipment that operators would need to wear, and they come in different levels based on the incident energies that could be that they could be exposed to. So in the EU, there's not really a specific standard, but in the States there is the NFPA standard.
Got you. So in the EU, it tends to follow sort of just general health and safety legislation, does it?
Just general health and safety legislations, which in those HSC legislations, they stipulate that you need to do a risk assessment. So this is where, right, so you need to do a risk assessment. And you're like, okay, so who's really good at doing risk assessments? In the States, they'd rather do risk assessments than actually just make it standardized across the board, you know, that you need to do this, which is really the American culture, right? It's less about less government, less oversight, less this, right? So there's one book, NFPA 70s for everything, arc flash power, but then they allow you to do risk assessments, right? Because they understand that every site is unique, every place is unique, so they don't want to put overarching standards. So that's one way. So we just adopt what the Americans are doing, and physics is physics. Thankfully, it doesn't change across the pond, so we can just bring that over and take and adopt it to the equipment here and use that analysis as our basis.
Are there ways that we can improve electrical design, you know, just to get rid of this challenge? I mean, you've mentioned designing in sort of sensors, like putting light sensors in and so on and so forth. But, you know, are there kind of some big gotchas that are being missed?
I don't think so. I think we're really tightening up loose ends. And if you know, like we talked about earlier, arc flashes are mainly due to human error, right? It's the whole point is to try and to cross that high voltage gap. To do that, it's not really easy. You really need a very small gap. And what normally happens, how that small gap is created, is when somebody drops something, right? So as it drops, it'll get close to the other electrode and create that small gap, an arc, and everything happens so quickly. So most arcs, most arc flashes are human error. So how do we mitigate human error? So it's, more training, more, you try and train and try and make people, in stressful situations, right? When this is happening, it's a stressful emergency situation. So how do you train your workforce to be able to deal with arc flash incidences? I feel is we've done everything we can with technology to try and mitigate it, right? So unless we remove the operators and have robots do it, maybe that's be the best.
Well, but then there is the question, should we be working on this stuff when it's live?
Exactly. Should we be working? I'm a proponent of why do we need to work on live equipment in the first place? But I do need to see that it's working, right? So, unless I do something when it's off, close the doors, put it on, it's not working. Put it off, try this, close the doors, put it on, right? So just the nature of how we work with things, right? I'm not going to work on a car engine with the hood closed. It's kind of, I'll need to run it to see certain things, to get certain measurements, to get certain information. Yes, I could use probes, I could use sensors and try and eliminate. And we do see that. We do see, where data center operators ask for remote, like a way to plug in with a cable and to remotely operate circuit breakers so you don't have to do stuff inside.
Sorry, I asked that question about why are we working on live equipment, because we were talking about ways to protect people from arc flash injuries and improving electrical designs in order to facilitate that. So in addition to ways to protect people themselves from arc flash injuries, what are some of the ways to improve electrical designs in order to reduce incidences of arc flash occurrences?
So the first thing you would do within the electrical design is to have selective coordination. So selective coordination is basically where you have the breakers, relays set in such a way that you want the relay closest to the fault to open, right? Because a fault cascades from the source. So wherever the source is, so if it's a nuclear power station, that's what's really providing the source for the fault. So everybody sees it in series. So you don't want the guy that's protecting the whole site to open. If that happens, you lose power to the whole site. So you select the breakers in such a way, the relays in the breakers or the trip units in the breakers in such a way that the closest one trips. Now, what you'll see in electrical designs, especially in data centers, is that you'll have a lot of breakers of the same size, right? So coordination becomes an issue. Now, when you have that, now zone selectivity is a problem. We introduce zone selective interlocking. Now, zone selective interlocking, like the name states, is where you still want the same principle of the breaker relay trip unit closest to the fault to react. Now, if all the breakers are the same trip units with the same characteristics, they'll all react at the same time. So what you do is you have them talk to each other. So there's a cable connecting all the breakers, and you have them zoned out, right? So zone selective interlocking, and they're interlocked such that the breaker closest to the fault will see it, and the guy upstream will wait and say, okay, buddy, I'm going to wait for you. I can see that something's happening, but I'm locked out until your zone clears. If you don't clear, then I'll go. And if I don't clear, the guy upstream will go. So you create zones with the controls of the relays. If that doesn't work, then you go down the arc resistive switchgear. Now, the thing with the arc resistive switchgear, there is arc resistive switchgear standards for MV equipment, and there are those for LV equipment. For MV equipment, it's more standardized because that's based on the AIC classification of the panel, which is basically the classification of the panel that it can take, that it can withstand an arc within the panel with either an operator in front of it, on the side of it, or the back of it. LV wise, there's not really a standard per se. There is a technical note provided by the, I think it's the IC, I believe. But there's not really a standard per se, but that note is still utilized within the industry as guidance as how to create arc flash resistant switchgear, and that's what we use as a basis to check whether a switchgear should be rated as arc flash switchgear. And then if that is, you make your switchgear as robust as possible, and then you add, if that is still a problem, you add digital technology. So there's sensors that you can add and additional arc relays just specifically for the arc, right? Because within a power system, you could have a short circuit, and this is what selectivity is for. Not all short circuits cause arcs. Remember, an arc is due to the ionization of the air, right? You have two electrodes, and the air in between, or the gas in between, is ionized. Now, you could just have a fault between two conductors or three conductors, and it's bolted and nothing happens, right? Because it doesn't cross over. There's no gap being bridged. So that's just a regular short circuit, and that could still be, that could cause shock, right? There's the other part where it could cause shock and could still damage equipment due to the electromagnetic forces that you'll experience at those high faults that could bend metal. So you could have faults that could bend the metal and bend the switchgear, and that's what selectivity is mainly for. And now we have the introduction of additional selectivity for arc flash instances. So I feel like those four measures, so selectivity, which will be done anyway due to the shock and the short circuit necessities, and then that also works with the arc flash, and then you'd now bring in zone selective interlocking, bring in arc resistant switchgear, or bring in additional digital technology in the form of light sensors and specific arc relays.
Are there any downside to introducing some of these improvements to electrical designs?
Are there any disadvantages? I guess the disadvantage would be the more systems, the more, I guess, measures you add, the more complexity you always add to your system, right? It's more information that the operators in the data center need to know about, they need to understand. So it's more information that you're already packing on the operators, and yeah, it's I think that's one of the downsides. It's just more stuff, and then also the cost of it. All these measures have additional costs to it. I think those are the two. The two negatives. At the end of the day, I don't. You're trying to make it more safe. So the safer you make it, the better you make it, in my opinion.
Okay, yeah. So, but cost and complexity comes into that, and then presumably, is there an impact on efficiency as well because the circuits are more complex?
Well, the circuit, I guess the circuitry remains the same. You're using the equipment within the circuitry, or the functionality within the circuitry, to make it work quicker. What happens is that, yes, you are sacrificing, like, for example, selectivity for human safety, right? So where you could lose more parts of your system. So you could end up losing more parts of your system, causing downtime that will have, other repercussions with your end users, and that, which is financial ramifications and all of that. But then you've saved a life, or you've, on the other hand, right? So
yeah. Is there an ROI you can ascribe to mitigation solutions?
Yeah, nothing happening. um, I mean, it's we at the end of the day, it's humans, right? We're dealing with humans. So if people feel that they're in a safer place, they'll work in a more comfortable in a more comfortable way, right? It's and and if this is implemented, with training, um, right, I feel that it'll bolster, or it'll make people want to be within certain spaces, right? Like, as a designer, sometimes I don't want to be within certain spaces because I know, okay, if this happens, I'm scared of, as an electrical engineer, I'm scared of electricity, or I respect electricity. So, but knowing that there's additional measures within a system gives me confidence that whoever who's running the data center cares a lot about making sure that the operators are safe, making sure that the equipment is the most, and it's the most robust, it's the most, I don't say it's not efficient, but I guess, as safe as we can make it, because at the end of the day, electricity is dangerous. And with data centers and with hyperscalar data centers, we are bringing in a lot of power. So we should be cognizant of that.
Yeah, got you. I mean, to be honest with you, I can't imagine going to work thinking, oh, the worst that's going to happen today is second-degree burns. It seems like an interest. Yeah, hats off to the people that do this kind of stuff.
I mean, exactly. Hats off to them, man.
Well, yeah, but obviously only when it's safe to remove your hat. What conclusions can we draw about arc flash? I mean, they are obviously a serious concern.
Yeah, they are serious concern, and thankfully there are mitigation measures in place to be able to improve our electrical designs to make sure that we mitigate arc flashes. Because just as we earlier talked about, the arc has a lot of heat, there's light, and there's also shrapnel from the shockwave that's released because of the metal that's between the metals in the electrodes. So if it goes wrong, it can really, really, really go bad. So having all these mitigation measures within the electrical design, and making sure that it's been done against the most current standards, because things do change as incidences happen. That's how the standards change. As incidents will happen, a couple of incidences will happen, they'll realize, okay, maybe we should now do this. There's been a pattern with this now. I believe that making the data center with the equipment that has additional arc flash mitigation will be a benefit down the line.
Got you.
Yeah.
So we should use things like arc resistant switchgear as standard, for example. Would you say?
At least.
Yeah.
So yeah. Use arc resistant switchgear, even though that they'll have, there's consequences to that. The switchgear will become bigger to be able to accommodate all this. But at the end of the day, human life, should supersede cost or complexity, I think.
Yeah. Okay. And cost in particular, because there are more data centers being built. They are becoming more expensive. I mean, I think I saw some stats the other day that the cost of data centers is increasing. I guess we can't really attach a value to a human life, can we? No amount of money is going to change something life-changing, for a family or whatever as a result of an arc flash incident. So
exactly.
But then we live in a commercial world, right? So there may be compromises sometimes.
Exactly. We live in a commercial world, and there's always going to be compromises. but but you don't let the compromise be big to a point, that it costs you and something else, right? But that's how we as humans, unfortunately, we wait until something wrong happens to fix it, even though we'll have Cassandras. So we are like the Cassandras, the consultants with the Cassandras. Nobody wants to listen to us, right? So Cassandra in Greek mythology was cursed by Zeus, that if she said the truth, nobody would believe her, right? Until the incident happens. So we're like Cassandras. So it's like the guys at NASA on the spaceship when the shuttle went up, and they were like, "Oh, just turn it around so we could see the bottom of it," because they I think they'd seen in the videos that one of the clay plates had fallen off. And the heads were like, "No, it's going to cost too much money. We'll have to reroute satellites. It's going to cost us too much." What happened to the space shuttle on reentry? It burned up. What happened after that? Every shuttle after that, when it launched to space, had to have its plates checked by satellites. So you see, so it takes disasters for us and incidences for us to implement things sometimes, unfortunately.
Yeah, well, they sound like they can be very expensive lessons sometimes, but it's good to know that as electrical designers that you're taking all this stuff very, very seriously and doing your utmost to protect human life.
We do exactly, and people when I talk about that as engineers, our financial hats should be the last one. People don't like hearing that.
Reuben, thanks very much for talking to us today. It's been very, very interesting.
Thanks for having me, David.